All right, welcome back to another episode. Today we're going to be talking about acidosis as well as electroneutrality. Okay, so anytime that you're approaching an acid-base problem or anytime you're approaching an acidosis, you must understand the concept of electroneutrality, which states that all the anions of the body have to equal the cations in the body. And so the most prominent cation in the body is, of course, sodium. The most prominent anion in the body is chloride, salt. Haha, who would have thought? The next most prominent anion is bicarb. Okay, so we kind of have a breakdown of the normal right here. And that's kind of how we derive our anion gap calculation. And so I just want to point something out really quick is that sometimes we have to correct for albumin. And so let's just conceptually understand why. So if albumin's concentration normally takes up this much of the other anions in the blood, and let's say that it's artificially reduced now to here, well, that's going to shrink this gap. Okay, so that's one way you can get a decrease in anion gap or an artificially low anion gap, but more to come on that later. I just want to point that out conceptually to understand. So another important rule to understand is that the body likes to normally trade chloride with bicarb. In other words, if the bicarb is reduced, then you'd expect the body to increase its chloride because it needs to maintain electroneutrality, right? And so if you're losing bicarb, you have a decrease in bicarb, you have a decrease in negative charges, which the body will try to absorb or increase its chloride concentration to maintain electroneutrality. All right, so let's take a look at an anion gap, or what occurs in an anion gap. So sodium, the cation concentration stays the same, right? But by definition, if we have an anion gap, metabolic acidosis, we're going to have a decrease in bicarb, but normally the body should do what, like I just said, is increase its chloride concentration to maintain. However, there is already negatively charged acids such as lactate, ketones, whatever, that are taking up that negative charge. So therefore, the chloride stays the same. And we see that here. And so you have this negatively charged anion that's taking up space to maintain electroneutrality. So let's do a quick example of what it would look like to have a non-anion gap acidosis. Let's just quickly draw this out. We have sodium here. And let's just keep the colors consistent. So this is our anions, our other anions that we have. Of course, our bicarb will be reduced. All right, so I just actually drew a high anion gap metabolic acidosis because look at this. This should normally be about this size, and we see an increase in the anion gap here. Oops. So this actually represents an anion gap acidosis that I just drew, but I'm glad I did because the point I want to make is that instead of this portion increasing the yellow portion, it would actually be chloride. That would be here instead. So then once we measure that anion gap, right, which is supposed to be normal here, increased here, and we'll just say this is normal here. Because again, we had that chloride now instead of that acid. Fill this portion and maintain electro neutrality.